Today, I will bring you a new product, an unpacking. I'm personally looking forward to it. Flexible current probe, or a Rogowski coil current probe. In recent years, more and more manufacturers are making this kind of flexible current probe, including some DIY products. Most of these products, they are benchmarked against big brands like PMK or IWATSU. Their product parameters are generally 30 MHz bandwidth. Today this product is from ZLPROBE. Their product is quite distinctive. Their latest product 50 MHz. So I'm particularly interested. Today, I will unbox it. Let's take a look at it and test its effect. It's a small bag. Now this lot of packaging is becoming more and more delicate. Its entire structure, it's kind of like this Mixit product. However, this integrator, it's a little bit bigger than Mixit's integrator. Because of this integrator by McCausson, it is to be connected directly to the adapter BNC port. I feel this size and weight may be larger, but I don't have Mixit's products. I can't make a comparison. This power adapter is 12 volts and 1A. This mouth is this small round mouth. It's a BNC adapter cable. This is a better review. It comes with a protective sleeve. Let's take a look at the integrator. It's HFC P1608 300 amps with an output of 1 to 50 megabits, a maximum of 1 bandwidth 12 volts power supply. It's an integrator of a metal structure. The metal structure helps with some shielding, because after all, he is an amplifier. Inside there are operational amplifiers and such. This is an indicator light and a display with a power supply. The BNC cable is part of the coaxial cable connected to the oscilloscope, and this Rogowski coil part, the feel is very close to PMK's. Like this contact part is made of a piece of plastic. I guess it's made by 3D printing. This is the feel of the mat, which is very non-slip. It is very suitable for here. And this plastic has one more of these protective sleeves than PMK. I have many of these PMK current probes in my company, but I don't remember wearing this cover. This coil of it is the entire Rogowski coil part and is the most fragile. So a cover with this protection would be better. Then this opening and this insertion of it are similar to PMK IWATSU. The box also has foam protection. The rest is a warranty card. There is also a manual, a list of basic electrical parameters and accessories. The one we tested is the HFC P1608 series, and the wire diameter of this is 1.6 millimeters, just enough to pass through the 2 pins of the TO-20. There are even finer probes of this type on the market. However, with a thin probe, its low-frequency response is difficult to do well. It's a little bit less robust. You can choose according to your needs. The circumference of this ring is 80 millimeters. It offers different models to meet different peak current requirements. It covers a range from 60 amps to 12,000 amps. Most of the products launched by companies are mostly within this range, such as PMK or Mixit. Typical application scenarios and appearance description. Take the SS-284A of IWATSU for a comparison test today. The basic parameters of the two are very close. It's just that the bandwidth of IWATSU is lower. The integrator design of this IWATSU unit is very large. The packaging of IWATSU is also very large. Relatively speaking, the packaging of ZLPROBE is much smaller. ZLPROBE adds a protective cover on the outside of the spiral coil, which is more flexible. It can play a protective role in normal times. If you need to measure in a narrow environment, the protective sleeve can be removed. We often see this kind of coil after a period of use. This outside of this coil, It's insulating. It will be damaged and we have to use tape to make a temporary repair. What's worse, the coil is directly broken, which is extremely difficult to repair. Iwasaki's current probe has a sign indicating the direction of the current on the side, so probe not have. I suggest adding such an identification. The Iwasaki adapter and its jack are bigger. A simple testing environment with nano VNA. Let's first take a look at its high band amplitude frequency characteristics. Focus on the bandwidth. After all, 50 megabytes. What you see now is the ZLPROBE 1. Its amplitude frequency characteristic curve in the high-frequency band is more reasonable. If we use 1 MHz as a baseline, its -3 dB bandwidth is about 56 MHz, between 43 and 45 megabytes on the curve. There is a discontinuity. We don't know if it's caused by the test environment. Let's take a look at this test result comparison of Iwasaki. In the same frequency band, also shows a little discontinuity, but it's not that serious. So this discontinuity may also be related to the testing environment. The bandwidth of Iwasaki is 28 MHz. Let's zoom in on this discontinuity point. Compare with others with more specialized equipment. Discover that this discontinuity should be real. However, the amplitude of this fluctuation is only about 1 dB, so it's not really a problem for extremely fine Rogowski coil current probes. The frequency response at the low-frequency band is also a very important parameter. We tested his -3 dB bandwidth at 14 Hz. This is very close to the measured value. On one of the calibration certificates he gave, I won the 50 turn to finally obtain this curve. In the low-frequency band, we need to increase the amplitude of the injected signal because its noise is mainly concentrated in the low-frequency band. Burst peaks are at 15 mV, consistent with the value on the calibration certificate given by ZLPROBE. We made a circuit, test different current probes, to see if their test results are consistent. We use this A63 autocurrent clamp for comparison. Here's a typical waveform of this circuit. Initial stage. Because our input voltage is relatively low, only 12 volts, its rising slope is relatively slow. There was an avalanche when the months were shut down. The MOSFET is 60 volts, and avalanche is close to 70 volts. It's going to come down at a very rapid rate. The LED inductance and the integrated capacitance of the months create high-frequency oscillation. This circuit is more suitable for use between different probes, whether the test results are consistent. Let's compare. Let's move them together. Amplitude of the Rogowski coil current probe is closer to our design value of 25 amps. A 6302 has not been calibrated for a long time. It's normal to have some deviations in the result. From the waveform point of view, the delay of the A6302 will be higher. This is just a system characteristic. It doesn't represent good or bad. Let's take a look at the difference in system delay. We can use the section with higher DNTT to see. Let's expand it. And then we call up a reference waveform. This reference waveform, we put its vertical position at 1. The current reference position is exactly 0. We save the reference waveform. Move it directly above the A6302 waveform, and we can see the delay difference between them. We measure the difference in its delay of about 7.2 nanoseconds. In the same way, we can see if the rising edge is also 7 nanoseconds. The rise time measured difference is 7.5 nanoseconds. Both results are consistent. Roach coil recommended for the ideal test orientation is that the conductor passes through its center perpendicularly. Especially in a narrow environment, we often fail to meet this optimal position. The next step is to test where the conductor passes through the center of the coil and the edge position. Test them and the results are not much different. The conductors go through the coil as parallel as possible. In addition to the above mentioned effect of a change in orientation between the wire and the Rogowski coil, I also tested a PTB. I chose a copper sheet with a fixed potential and high DVDT copper sheet for testing the above-mentioned 5 situations. After each test of the current waveform, I will save it to a specific reference waveform. A total of 4 channels of reference waveforms were used, and then the last test result. They perfectly overlap. I couldn't see any difference. This test result still surprised me. The high dVdt test results for Rogowski coils have an impact, so some models claim to be able to withstand high. I don't see dVdt in its datasheet. To see the relevant parameters, we will select different points on the circuit board. Let the Rogowski coil approach different points. These points have different dVdt's. Let's take a look. When the Rogowski coil is near different dVdt points, what kind of change its output will have? We selected 4 points, which are labeled as A, B, C, and D in the circuit diagram. The size of dVdt is gradually decreasing. The result shows that the consistency of this association is very high. This test is just to remind everyone to pay attention to the impact of dVdt. Most probes are not currently labeled with this parameter. Finally, let's take a look at 50 mega 300 amps of PEM for this product. That is, the ZLPROBE 1, which is directly comparable to this product. Looking at these parameters from left to right, its noise level, the peak of 10 mV will be lower. Let's look further. We find that it's -3 dB bandwidth. At 50 MHz, it is much worse than the ZLPROBE 1. That is to say, it may have sacrificed the low frequency bandwidth to obtain this relatively low noise. We know that Rogowski coil current probe noise mainly concentrated in the low frequency band. Therefore, if we increase the low frequency cutoff frequency, it should reduce its noise. But this is very awkward. Because 50 Hz to 3 dB bandwidth, it cannot test the power frequency current. Simply comparing these two parameters, definitely choose the ZLPROBE this one, because its low frequency advantage is too great. The power frequency signal cannot be tested. PEM this one, its size remains the same. Besides being inconvenient to carry, it makes the experimental table look more messy. Of course, we also understand that if you want to change the products of big companies, they have more concerns. That's all for today's video. Thank you for watching. See you next time.